All right, hello and welcome back, ALEKS students. So this is another requested video, so thank you very much for the request. I'm always happy to do these as long as I've got time. And so this is a topic that's called using the maximum work theorem with chemical work. This is a pretty challenging topic. I am going to make two different videos. This is going to cover the more basic instance of this topic, and then the next video will be sort of the more advanced, annoying type version where there's a lot more going on. So in this one, I want to just cover really the basics and really hit on the take-home message here, what this topic is all about. And I know that when you look at this and you see the words chemical work, that can be somewhat confusing. You might have flashbacks to physics if you're talking about work in physics, and we all know that that's super confusing. But in this case, what we're talking about is chemical work, which is really just a type of energy. And I think that that's really the take-home message here. We're talking about a transfer of energy in all of these types of problems. We're talking about one reaction is going to give off energy, and then another reaction or another process is going to absorb that energy or sort of use that energy to do work, to create something new, essentially. The other thing that we need to keep in mind is that there's a relationship between work and delta G and this Gibbs free energy. And so basically, again, I think sometimes these inequalities can be a little bit confusing. But we can focus on the aspect of this where work is going to be equal to or less than, but that's only if we're losing energy, but if we're not efficient. But if we're perfectly efficient, the work is going to be equal to negative delta G, the free energy that's released in that first chemical reaction. So if we look at this instance in particular, we're going to start with glucose, and our body's going to use up glucose. It's going to react with oxygen. That's why we breathe in oxygen, right? And then we breathe out CO2. This is a reaction that's happening in our bodies. And as this is happening, we're going to be releasing some amount of energy, right? So for every 1 mole of glucose, we're going to release 2,872 kilojoules of free energy, right? So that's what that Gibbs free energy is. Now, in this process, we're told that the Gibbs free energy formation of one peptide bond to create a new peptide bond to join one amino acid to another to create a protein is 21 kilojoules per mole. And so you might be looking at this and sort of saying, what sort of information is that going to give us? What use is that? We'll keep reading, trying to unpack this, but that's something that I've underlined. The next thing says some cells are assembling a certain protein made of 90 amino acids. Now, there's this note that's, again, a little bit confusing, but the take-home message is if you have 90 amino acids that you want to bond together, what this is saying is that you need to form 89 bonds. And that's these one amino acid to another, these peptide bonds. We need to form 89 of them. Each one of them requires 21 kilojoules per mole of energy to create. And if we want to build this protein with 90 amino acids, we're going to need to form 89 bonds. That's what this sort of note is basically saying. So then it says, calculate the maximum moles of this protein. So that's what we're looking for, the maximum moles of this protein that can be assembled if 150 milligrams of glucose are available for combustion. So this is where that transfer of energy is going to come in. We're going to consume this 150 milligrams of glucose according to this chemical reaction up here, and that's going to give off some energy. Then we're going to use that energy and apply it to the formation of these peptide bonds in order to start building up this protein, and we're trying to figure out how much of that protein we can create with the amount of energy that's going to be released from this 150 milligrams of glucose. So hopefully that all makes sense. Let's go ahead and get started with the calculation. So the first thing I'm going to do is I'm going to convert this 150 milligrams of glucose basically into moles of glucose, because I know that this chemical reaction, it's almost like a thermochemical equation, right? We've got 1 mole is going to give off this amount of energy. We're just talking about free energy here instead of an enthalpy, but I want to convert this to moles. So the first thing I'm going to do is I'm going to convert it to grams. I think that that's usually a little bit easier, and I actually like to write things out. So I'm going to write out 1 gram over 1,000 milligrams, right? So then my milligrams are going to cancel. And then that gives me 0.150 grams of glucose. And then I'm going to convert this grams of glucose into moles of glucose. So times, make sure we can still see everything, 1 mole of glucose over, and then I calculated this C6H12O6. The molar mass is 180.18 grams. So that's just adding up, 12.01 times 6, 1.01 times 12, so on and so forth. You get this 180.18. So then that's going to be 8.33 times 10 to the minus fourth moles of glucose. So that's the number of moles of glucose that we have to react, right? We have to burn or to, use up in this chemical reaction. And that's going to release some amount of energy. So essentially what we want to do is we want to convert this moles of glucose into amount of free energy. And so again, there's different ways to do this. I actually like to write it out as if it's a dimensional analysis type problem. So I'm going to write out 8.33 times 10 to the minus fourth moles of glucose times, so for every reaction, this is going to be minus 2.872, and we'll talk about the signs here in just a second, but I'm just going to bring this number down for every 1 mole of glucose, right? And so then I know that this glucose, this is glucose here, so every time we consume 1 mole, this is the amount of free energy, and so then we can calculate that. That's going to give us 2.391 kilojoules released, and I'm just going to use the word released here, or maybe we'll just say available. So this number here, 2.391 kilojoules released / available, I'm saying that because of this negative sign here, right? So basically the importance of this negative sign up here, means that energy is going to be released, just like an exothermic reaction. It's going to be energy that's available to then be used in another process. So I'm going to sort of, be a little bit lazy about my sign here because I know, like if we do the calculation, right, you should say, well, there's a negative here, but I'm just going to write released because I know that energy is available to be used. Okay, and I'm just going to leave it as a positive value. So now we have this amount of energy that's going to be released, and we want to use that energy to form these bonds. And we know that for every one, it takes 21 kilojoules per mole for one of these, and we need to form 89 of them. So we can just sort of do a quick calculation where it says 21 kilojoules per mole, and that's for one, times 89 bonds, because that's going to be, we need to form 89 bonds per protein, right? Per protein. And that's going to tell us that for each one of these, we're going to need, or for each mole, we're going to need 1,869 kilojoules per mole. This is going to be the amount of energy needed to form 1 mole of protein. So let's write that out. So this is energy required to form 1 mole of protein. So hopefully that makes sense, where I'm getting these numbers from. 21 kilojoules per mole for each bond. I need to form 89 bonds because 90 amino acids are going to be put together. To put 90 amino acids together, we need to have 89 bonds holding them together. And then that's going to be the total amount of energy required to form 1 mole of protein. So this is the amount of energy for 1 mole. This right here is the amount of energy that we have available, right? This is the amount of energy that was released. And what we're doing here is a transfer of energy. So basically, I'm just going to combine these two numbers to figure out, well, if this is the amount of energy that I have, this is the amount of energy that's required for 1 mole, how many moles can I sort of generate essentially? So again, I like to write it out just sort of as a dimensional analysis problem. 2.391 kilojoules times 1 mole. So I'm going to use this essentially as a conversion factor, more or less, 1869 kilojoules. We'll see that my units of kilojoules will cancel out. And then that will give me 0.001279 moles of protein that I could form with this amount of energy that was released from reacting that glucose. So then we need to convert to 2 sig figs. So then the answer would be 0.0013 moles. So that's my final answer. And just sort of to walk us back through the process, this one, it's not as difficult, it's not as challenging. We've got our take-home messages up here. We converted our mass of glucose into moles of glucose. We used our moles of glucose to figure out how much energy is going to be released / available to be transferred to our other process in this reaction. That other process is the formation of these peptide bonds. I know that because each bond requires 21 kilojoules per mole of energy, we've got 89 bonds for our protein. Then I can sort of do this calculation here to figure out, well, it's going to require 1,869 kilojoules per mole. And then just using this as a conversion factor, this is the amount of energy that's available. And this is the number of moles I can sort of generate in this process. So that's our final answer. And I will be doing another version of this, a slightly more challenging version, if this one wasn't challenging enough. All right, stay tuned.